Good morning, Assalamualaikum, and good morning, everyone. Can you hear my voice?
Introductor again.
All right. Okay. Let's continue with our class. So from previous class, right, we find the solution for this derivative, right? F prime x is equal to fx, and we have the initial condition. The f0 is equal to 1. And then we know that its exit solution is actually fx is equal to exponential of x. And then we calculate the exit solution and also the backward fx, and also the using the backward approximation. Right? Now, if we are to plot this on a graph, this is x axis and this is fx. Let's say the black one is the exact solutions. Then let's say the red one is the forward. Is the backward. This is x0, x1, x2, x3, x4, x5. Now, how do we calculate our approximation error? Our error is this difference. The difference between our approximations and also the exact solutions is what we define as our approximation error. Error. But as I show you last week, not last week, on Monday, if we increase our n in the divisions, its accuracy will increase, right? Meaning that our delta fx is approaching 0 and also delta x is approaching 0. The approximate solution will be closer to the exact solutions. Right. If let's say in these solutions we use n is equal to 10, maybe we will get this kind of solutions. This is for n is equal to 5, n is equal to 4, 4 divisions, 5 points, and n equal to n, right? With 11 points. Okay, so far, any questions regarding this? And this is what we call convergence. And convergence is one of the method that we use to determine our approximation, whether it's good or it's bad. Okay. Let's say we do not know our exact solutions. So how do we find our convergence? Okay. Let's say we do not know the exact solutions. How do we find? How do we evaluate the convergence? Let's say we plot our graph.
Excuse me, doctor.
Yes?
You haven't recorded the session.
Is it? Okay, okay, thank you. Okay, I'll record it now. All right, thank you. Let's continue. So this is fx and this is x. Right, let's see. At first, we use n is equal to 5. And our solutions become like this. This is for n equal to. And then, let's say we use n equal to 20. And then we plot our solution again, but we use a much more number of points. The n equal to 100. And then we increase some more of our points. Green one is n is equal to maybe 300. So we can see that for n is equal to 100 and n is equal to 300, the solutions do not give much difference. So by this, we can also evaluate our convergence. Okay, so in numerical methods, more points to use may means higher accuracy. But bear in mind, with more point and higher accuracy, you will increase your computational time. Therefore, in practical usage, we will find the most suitable number of divisions. And in this case, right, we might just use n is equal to 100. Okay. Any question regarding convergence? All right. If you have any questions, you can ask me now, or maybe you can also ask later. This is computation time. Sorry, I will write it clearly, more clearly. Yeah, it's more times to calculate. Your program will run longer. Let's say it takes 5 seconds for n is equal to 5. It might take 100. It might take 1 hour for n is equal to 300. Okay. Sometimes numerical calculation can take up to days and maybe months. That is why finding the most suitable number of points is important. This is only for your knowledge, but for the purpose of our course, we will just use the n is equal to 5, n is equal to 10. We won't calculate using hands for more than that, right? Right. Any more questions? Right. If there are no other questions, now we will look at um, approximations of derivative. First order derivative. Like Um, see, last week we have forward difference, right? One, right? We have forward difference. So forward difference in forward difference approximations. Let's say we have our fx function. This is our xi, point of interest. This is our xi, xi. Our derivative here, f over dx equal to of xi plus delta x minus I divided by delta. And then we have, for the second one, we have our backward difference approximations. So again, we plot our function fx is x delta is xi. So our approximation for derivative of fx is equal to f xi minus f I minus delta x then we have another one that is central. So difference dimensions. So for central difference, we have xi minus delta x. Also, we have I plus delta system I plus delta x I delta. So our approximations will be right. Is right. F dx is equal to I plus delta x 2 delta x. So you can see that xi our point of interest and delta x is our step size. Okay, now let's go back to our forward difference. So you see in forward difference, we calculate our point of interest based on its current value, right? But for backward difference approximations, the point of interest is calculated based on its previous um, previous state, right? So forward difference also, uh, we call it as implicit, and backward is often called as explicit. Explicit approximations, it can handle usually a large step size. For implicit, usually we need a small step size. Like we see in our example here, is right when we use our forward as its implicit, um, the solutions of our approximations is not far away from our exact solutions, but the explicit give a much uh, uh, but the backward approximations is not very accurate, right? So far, any questions? No questions. Okay, now we'll go to the next part of our class today, that is truncation error. How do we derive actually? How do we derive FD approximations? So we derive our approximations from Taylor series. Did you all still remember your Taylor series? Say for this function f, x plus delta x equal to f prime. Two or on, right? This is Taylor series. Since we want to find the approximations for this, so we truncate the rest of the Taylor series. And these solutions become to rearrange these equations. So what is our truncation error? So our truncation error is 2 square pi. So because our truncation area involve the term delta x and higher, so we say that the order of our truncation area is delta x. Right. Now, for your homework, find the TE for backward and central difference. Right? Find of delta O, actually O, order. It means order. Right? Translation area is in the order of delta X. Right? See how you find the TE for backward and central difference. And let's take a break for 10 minutes. All right, you can ask if you have any questions. Okay. Okay, truncation error is that when we derive our finite difference approximations using the Taylor series, since we only want the approximations for the first derivative of fx, for this term only, right? We just want the approximation for this value, we truncate, meaning we take away the other rest of the equations. So this part, what we call the truncation error. Okay, is that clear? Just by considering this part of the Taylor series, we get our finite difference approximation formula. But in the previous to formulate it, we truncate some of its value. So this is the truncation area. So how we determine the truncation area is that the term here, the term that we remove here, we divide by delta x. That is why we get our truncation error as this one. And since the lower order of our error is the delta x, and then higher, right? Delta x and then delta x squared. And delta x is should be 3 over 4, maybe, oh, right? So we take that the truncation error is of order delta x, because usually in numerical methods delta x is small, is smaller than 1. So the square of delta x is smaller than delta x. Right. So this is the reason why We call that the truncation area is the order of delta x. Okay, now how about the backward? So how about our backward formulations? Alright. So similarly for backward approximations, the translation error is also of the order of delta. So how about the central difference approximations? For central difference, for central difference, the TE is of order delta x square. So TE order of the x from this we can say that central difference coordinations as smaller TE cos delta x squared is then delta cos usually less than right. So far any question? I think this will conclude our class today. So far any questions? And one more thing. Please let me know if the class that you are having before my after my class is conduct face to face. So if the class after me conduct the class face to face, we may also conduct the class face to face, right? Because in the timetable, it's basically in the same place, I think, in the same, yeah, MEK1 or MEK2. All right. I think Taylor series should be something like X is equal to the third term in Taylor series in the fourth term is 2, 3. Three. So if you have any questions, you can ask. If not, you can leave and prepare for the next class. So I'll see you again tomorrow morning, same time. Bye bye and thank you. Right, thank you.
Doctor,
Yes.
wait, are you telling me the class is over already?
Yeah, the class is over. It's just 8 to 9 class.
Uh, okay.
Okay, I'll see you again tomorrow. Tomorrow morning, same time.
Sure, doctor. Okay.
Okay. Okay, thank you. Bye.